Welcome back to another math lesson hosted by Book and Table. I am your math tutor, Maurice Wright, and in this chapter, we are going to review complex numbers. We will discuss the equality rule, the basic operations, addition, subtraction, multiplication, and division, including working with conjugates. We'll discuss factoring that leads to roots that are complex numbers. And then we'll wrap things up by discussing graphing, including how to calculate both the modulus and the argument of a complex number in each of the four quadrants. Should you have any follow-up questions, feel free to leave them in the comments section, or you can contact a tutor in your neighborhood by visiting bookandtable.com or by downloading our app on the App Store. So to discuss complex numbers, we will have to discuss both real numbers and imaginary numbers. Real numbers can be found on a number line, such as this one, and include all integers, such as -10, -5, +5, +8, fractions, such as -2/3 or 33/7, and irrational numbers, such as the square root of 2. But what we won't find on a number line are imaginary numbers. Imaginary numbers are not considered real numbers since they cannot be found on the number line. So for example, two numbers that can be found on the number line are negative square root of 9, or -3, and the square root of 9, or +3. 9i, which is equal to the square root of -9. That is not equivalent to negative square root of 9. This negative's on the inside, this one's on the outside. Same thing over here. Our radicand 9 is positive. This one it's negative. So in neither case would our imaginary number be found anywhere on this number line. So it is a different kind of number. The imaginary unit I is equal to the square root of -1 and can be used to remove the negative from a radicand, such as the -9 we just saw. So the square root of -9 is equal to the square root of 9 times the square root of -1. Since any two radicals can be multiplied, that means we can break up this radical, or the radicand specifically, into two of its factors. So when we have a negative radicand, we can break this up into two factors, the -1, so we take the negative out, and then whatever the integer was. So by doing that, the square root of -9 is equal to the square root of 9. So now we can find the square root for this radical, which would be 3. And we have the imaginary unit, the square root of -1, which is I. So we can find the square root of a negative radicand, except in this case it will lead to an imaginary number instead of a real number. Same thing if we had the square root of -16. The square root of -16 is equal to the square root of 16 times the square root of -1. By doing so, we can simplify this radical. The square root of 16 is equal to 4, and the square root of -1 is our imaginary unit I. So we would get 4i. So now that we know what imaginary numbers are, we can discuss complex numbers, which combine a real number and an imaginary number. The standard form of a complex number has a real number a and an imaginary number bi. So for example, 4 plus 8i is a complex number. We have our real number 4 and our imaginary number 8i. The real number and or the imaginary number can be negative as well. So -6 is our real number here, and -10i is our imaginary number here. Now complex numbers in an equation actually act the same as regular expressions. So if two complex numbers are equal, then the real numbers are equal to each other and the imaginary numbers are equal to each other. So it's almost like we combine two equations into one. So 5 minus 6i is equal to x plus yi. So in this equation, the real number 5 is equal to the real number on the right side, x. So 5 is equal to x would be one of the equations here, our real equation. And now our imaginary equation would be negative 6 is equal to y. The I is found on both sides, so we can drop it as far as if we're trying to solve for y, for example. But in any case, our second equation involves our imaginary numbers. Our first one involves our real numbers. The equality rule just lets us know that whatever's on the left side equals whatever's on the right side when we have an equal sign, just like a normal equation. Except you must remember that on the left side, the real number is only equal to the real number on the right side, and the imaginary number or expression on the left side is only equal to the imaginary number or expression on the right side. So you'll deal with them separately when solving for variables. So for example, let's say you were asked to solve for x and y and then check the answers, and you were given the equation x minus 2 plus y plus 4i is equal to 8 minus 10i. So on the left side of our equation, we have an expression that represents our real number. This will be equal to our expression for the real number on the right side. Same thing with the imaginary numbers. The expression on the left side that represents our imaginary number equals the term on the right side that represents our imaginary number. So the first thing that we will want to do is step 1, set the real numbers equal to each other. So we have x minus 2 is equal to 8. And now by removing the imaginary numbers from this, we can solve for x. So we'll want to add 2 to both sides to isolate x on the left side. And 8 plus 2 shows us that x would be equal to 10. And now we'll find y separately. So step 3, set the imaginary numbers equal to each other. So on the left side, the expression that represents our imaginary number is y plus 4. And on the right side, it would be negative 10. We can leave the i's out. So we have y plus 4 is equal to negative 10. And now we'll want to solve for y. So we'll subtract 4 from both sides, leaving us with y is equal to negative 10 minus 4, which would be negative 14. So we got y is equal to negative 14 and x is equal to 10. So now the last step would be to check the answers by plugging them into the original equation. X minus 2 plus y plus 4i is equal to 8 minus 10i. So we plug in x is equal to 10 here, and we plug in y is equal to negative 14 here, and that gives us 10 minus 2, which would be 8. So the real number on the left side is equal to the real number on the right side, so that checks out. So x is equal to 10. And when we plug in negative 14 for y, we get negative 14 plus 4. That would give us negative 10i. And the imaginary number on the left side, negative 10i, winds up being equal to the imaginary number on the right side, negative 10i. So that confirms that y is equal to negative 14. So again, the equality rule is just a rule that helps us understand that complex numbers wind up working similarly to normal equations. You set the real numbers equal to each other and solve for the variable. You set the imaginary numbers equal to each other and solve for the variable. And then you can check the answers by plugging them back into the original equation. Let's have you try a few practice questions. Solve for x and y. Check the answers. Question number 1. X plus 6 plus y minus 5i is equal to 13 minus 7i. Question number 2, x minus 4 plus 2y plus 1i is equal to 20 plus y minus 6i. And question number 3, 2x plus 2 plus 10 minus yi is equal to x plus 4 plus 2y plus 4i. Pause the video, answer these questions, and then press play when you are ready to begin. Question number 1, step 1, set the real numbers equal to each other. So on the left side we have x plus 6 as the expression that represents our real number. And on the right side we have 13 as our real number. So we have x plus 6 is equal to 13, and now we solve for x by subtracting 6 from both sides, giving us x is equal to 13 minus 6, which would be 7. So we solve for x, and now we can solve for y by setting the imaginary numbers equal to each other. So that gives us y minus 5 is equal to negative 7. We can leave the i's out. And now we can solve for y by adding 5 to both sides. Negative 7 plus 5 gives us negative 2. So we wind up with y is equal to negative 2. So now we know x is equal to 7 and y is equal to negative 2. So step 5, we could check the answers by plugging them into the original equation. X plus 6 plus y minus 5i is equal to 13 minus 7i. So for x, we plug in 7, giving us 7 plus 6, which would be equal to 13. And that's the same number on the right side, so that checks out. For y, we have negative 2, giving us negative 2 minus 5, which is negative 7i, as our imaginary number on the left side. And that's equal to negative 7i, the imaginary number on the right side. So that confirms that the answer to question number 1 is x is equal to 7 and y is equal to negative 2. Question number 2. Step 1, set the real numbers equal to each other. So that gives us x minus 4 is equal to 20. We then want to solve for x, so we'll add 4 to both sides. 20 plus 4 is equal to 24. So we get x is equal to 24. And now we solve for y by setting the imaginary numbers equal to each other. So that would be 2y plus 1 is equal to y minus 6. And now we want to solve for y. So we'll start by subtracting y from both sides. So we get rid of the y on this side, and now our y is just on one side. 2y minus y gives us y, plus 1 is equal to negative 6. And now we'll subtract 1 from both sides to isolate this y on the left side. Negative 6 minus 1 is negative 7. So we get y is equal to negative 7. And now that we know the values for both x and y, we can check the answers by plugging them into the original equation. X minus 4 plus 2y plus 1i is equal to 20 plus y minus 6i. So we plug in x is equal to 24 here, and we get 24 minus 4, which is equal to 20. And the real number on the left side, 20, equals the real number on the right side, 20. So that confirms that x is equal to 24. And for y is equal to negative 7, we plug that in here and here. giving you 2 times negative 7, which is negative 14. Negative 14 plus 1 is equal to negative 13, I. And on the right side, we have y minus 6, which would be negative 7 minus 6, which is equal to negative 13, I. So the imaginary numbers are the same on both sides, negative 13i and negative 13i, thus confirming that y does equal negative 7. Question number 3. Step 1, set the real numbers equal to each other. So we have 2x minus 2 is equal to x plus 4. And now we want to solve for x, so we'll start by subtracting x from both sides. So we negate x on one side and just bring the x's to one side. 2x minus x is equal to x minus 2 is equal to 4. And now that we've done that, we have x minus 2 is equal to 4. So the next thing we'll want to do is add 2 to both sides to get rid of this number, negative 2. When we do so, 4 plus 2 is equal to 6. So we get x is equal to 6. Step 4, set the imaginary numbers equal to each other. So that would be 10 minus y is equal to 2y plus 4. And now we want to solve for y. So we'll start by adding y to both sides. That will get rid of y on the left side. Negative y plus y would be 0. So we'll have our y's on just one side. So that gives us 10 is equal to 2y plus y is 3y plus 4. And now that we only have one y in our equation, we can isolate our y the way we normally would. So we first want to get rid of this 4 by subtracting 4 from both sides. 10 minus 4 is equal to 6, and that's equal to 3y. To get rid of the coefficient 3, we'll divide both sides by 3. 6 divided by 3 is equal to 2. So we get y is equal to 2. And now check the answers by plugging them into the original equation. 2x minus 2 plus 10 minus yi is equal to x plus 4 plus 2y plus 4i. You could check x by plugging it in here and here, giving you 2 times 6, which is 12. 12 minus 2 gives you 10. So the real number on the left side is 10. And on the right side, we have 6 plus 4, which would be equal to 10. So the real number on the right side equals the real number on the left side, which means x does in fact equal 6. And for y, we plug in 2 here and here, giving us 10 minus 2, which would be 8i on the left side. On the right side, 2 times 2 would give us 4. 4 plus 4 would give us 8i on the right side of the equation also, thus confirming that y does in fact equal positive 2. So that is the equality rule. Let's now begin discussing the basic operations to complex numbers. We'll kick things off by discussing addition. Complex numbers are added by adding the real numbers together and by adding the imaginary numbers together. So let's say we had a plus bi being added to c plus di. So in each one we have a complex number, a real part, and an imaginary part. So you would add a plus c, the real numbers, and then you would add that to the sum of the imaginary numbers, bi plus di, which would become b plus d times I. So for addition, add the real numbers together, add the imaginary numbers together. So let's say you're asked to find the sum of 3 plus 7i plus 5 plus 2i. Step 1, add the real numbers. So the real number in the first complex number is 3, and the real number in the second complex number is 5. So we add those together. 3 plus 5 would give us 8. And now the second step, add the imaginary numbers. 7i is the imaginary number in the first complex number, and 2i is the imaginary number in our second complex number here. So when we add those, 2i plus 7i gives us 9i. So the sum of 3 plus 7i plus 5 plus 2i would give us 8 plus 9i. So for addition, add the real numbers and then add the imaginary numbers. Let's have you try a few practice questions. Question number 1. Find the sum of 4 plus 6i plus 2 plus 7i. Question number 2. Negative 2 plus 10i plus 11 minus 8i. And question number 3. 3 minus 5i plus negative 6 minus 4i. Pause the video, answer these questions, and then press play when you are ready to begin. Question number 1, step 1, add the real numbers. So we had 4 plus 6i plus 2 plus 7i. So our real numbers are 4 and 2, which would give us 6. The second step, add the imaginary numbers. 6i plus 7i gives us 13i. So the sum of 4 plus 6i plus 2 plus 7i is 6 plus 13i. Question number 2. We were asked to find the sum of negative 2 plus 10i plus 11 minus 8i. Step 1, add the real numbers. Negative 2 plus 11 is equal to 9. Step 2, add the imaginary numbers. 10i minus 8i is positive 2i. So the sum of negative 2 plus 10i plus 11 minus 8i is equal to 9 plus 2i. In question number 3, we were asked to find the sum of 3 minus 5i plus negative 6 minus 4i. Step 1, add the real numbers. 3 minus 6 is equal to negative 3. Step 2, add the imaginary numbers. Negative 5i plus negative 4i is equal to negative 9i. So the sum of 3 minus 5i plus negative 6 minus 4i is equal to negative 3 minus 9i. So that is how you add complex numbers. Let's now discuss subtraction. Complex numbers are subtracted by subtracting the real numbers from each other and by subtracting the imaginary numbers from each other. So if you had a plus bi minus c plus di, since you are subtracting a term with two parts, you will need to distribute this negative 1 to each term inside of this complex number, both the real number and the imaginary number. And the result will wind up being negative c and negative di. So then we wind up having a minus c plus bi minus di, which would be b minus d times I. And we add those sums together since we've already distributed this negative 1. So let's take a look at an example to help this become a little bit clearer. Find the difference of 4 plus 6i minus 2 plus 8i. So step 1, you want to distribute this subtraction is equal to -1 times each number in here. So you want to distribute the -1 to the second complex number. So -1 times 2 is equal to -2. The coefficient here is +1. Anything times 1 is just itself. So we don't need to do anything to this complex number, so we bring this down. So we have 4 plus 6i minus 2. And now we distribute the -1 to +8. -1 times +8i is equal to -8i. So after we've distributed the -1, we wind up with 4 plus 6i minus 2 minus 8i. So we have 2 real numbers and 2 imaginary numbers. So the second step is to combine the like terms. So we combine our real numbers 4 and -2, giving us 4 minus 2. And we add that to the sum of 6i and -8i. We'll be adding the sum of our real number and the sum of our imaginary number, since we've already distributed the -1 or our subtraction. So 4 minus 2 gives us a real number of 2, and 6i minus 8i gives us an imaginary number of -2i. So the difference between 4 plus 6i and 2 plus 8i is 2 minus 2i. Let's have you try a few practice questions. Question number 1. Find the difference of 16 plus 7i minus 9 plus 4i. Question number 2. Find the difference of -4 plus 5i minus 2 plus 6i. In question number 3, find the difference of -7 minus 9i minus 11 plus 3i. Pause the video, answer these questions, and then press play when you are ready to begin. Question number 1, step 1. Distribute the -1 to the second complex number, 9 plus 4i. -1 times 9 gives us -9. -1 times 4i gives us -4i. So we wind up with 16 plus 7i minus 9 minus 4i. The second step is to combine the like terms. So we combine our real numbers, 16 and -9. And then we combine our imaginary numbers, 7i and -4i. So that gives us 16 minus 9, which is equal to 7, plus 7i minus 4i, which is equal to 3i. So 16 plus 7i minus 9 plus 4i is equal to 7 plus 3i. Question number 2. We're asked to find the difference of -4 plus 5i minus 2 plus 6i. Step 1, distribute the -1 to the second complex number, 2 plus 6i. -1 times 2 is equal to -2. -1 times 6i is equal to -6i. So after we distribute the -1, we have -4 plus 5i minus 2 minus 6i. So our real numbers are -4 and -2. So when we combine the like terms, we get -4 minus 2. And then we add that to the sum of 5i minus 6i, which would be 5i minus 6i, which is -i. So -4 plus 5i minus 2 plus 6i is equal to -6 minus I. In question number 3, we were asked to find the difference of negative 7 minus 9i minus 11 plus 3i. Step 1, distribute the negative 1 to the second complex number. Negative 1 times 11 gives us negative 11. Negative 1 times 3i gives us negative 3i. So after the first step, we have negative 7 minus 9i minus 11 minus 3i. So the second step is to combine the like terms. So our real numbers are negative 7 and negative 11. Our imaginary terms are negative 9i and negative 3i. So that would give us negative 7 minus 11, which is negative 18, plus negative 9i minus 3i, which is negative 12i. So negative 7 minus 9i minus 11 plus 3i is equal to negative 18 minus 12i. Now let's discuss how we multiply complex numbers. Both real and imaginary numbers can be multiplied times real and imaginary numbers. Here's what I mean. Let's say we have a complex number 3 minus 6i. We can multiply it times 2, a real number. We multiply 2 times the real number 3, and that gives us a real number 6. We multiply 2 times the imaginary number, negative 6i, and that gives us negative 12i. So we can multiply a complex number times a real number, and the product is a complex number. We can also multiply a complex number by an imaginary number, such as 2i, giving us 2i times 3, which is 6i, an imaginary number, and 2i times negative 6i, which gives us negative 12i squared. I squared is equal to negative 1. And negative 12 times negative 1 would give you positive 12. So we wind up with a real number, positive 12, and an imaginary number, positive 6i. So this is a complex number. So we can multiply a complex number by a real number or an imaginary number, and the product will wind up being a complex number. Now let's discuss the imaginary unit a little bit further. The imaginary unit is equal to the square root of negative 1. I is equal to the square root of negative 1. So I squared is equal to the square root of negative 1 times the square root of negative 1, which is equal to negative 1. But the imaginary unit goes through a cycle up to 4. So I cubed is equal to the square root of negative 1 times the square root of negative 1, which would be equal to negative 1 times the square root of a negative 1. And this would be equal to negative I. So I cubed is equal to negative I. And then I to the fourth is equal to the square root of negative 1 times the square root of negative 1, which is negative 1, times the square root of negative 1 times the square root of negative 1, which is negative 1. Negative 1 times negative 1 is positive 1. And then once we get to I to the fifth is equal to I to the fourth times I. So that would be 1 times I. So I to the fifth is equal to I. So every 4, it repeats itself. Now, for most complex numbers, you'll only wind up dealing with I squared, but I wanted to make sure we reviewed this briefly in case your instructor gets creative. But let's take a look at the FOIL method in case we were asked to multiply two complex numbers times each other rather than a real number or imaginary number being distributed to a complex number. So the FOIL method is a technique used to remember the steps required to multiply two binomials. Remember, a complex number is a binomial. So if we are multiplying two complex numbers, we will need to know how to multiply two binomials. So FOIL stands for first. So you multiply the first term in each set of parentheses. So if we had a plus b times c plus d, the first thing you do is a times c, which is ac. Then the O stands for outside. So you're multiplying the outside terms, a times d, which will give you ad. So after the first two steps, we've multiplied the first term in our first binomial times each term in the second binomial. And now the third term inside means you're multiplying the inside terms. So notice now we are taking the second term in our first complex number, and now we are about to multiply it times each of the terms in the second binomial. So again, I in FOIL stands for inside, which means we're multiplying the terms on the inside. So b times c gives us bc. And then the L in FOIL stands for last, which means we're multiplying the last term in each binomial, which will give us b times d, which is bd. So we wind up multiplying the first term in the complex number times each term in the second complex number, ac and ad. And then we wind up multiplying the second term in the first complex number times each term in the second complex number, giving us bc and bd. Let's take a look at an example. Let's say you were asked to find the product of 2 plus 3i times 4 plus 5i. The first thing you want to do is use the FOIL method to expand the expression. So F stands for first, which means we're multiplying the first term in each complex number. 2 times 4 gives us 8. The O in FOIL stands for outside. So now we're multiplying our 2 times the second term in the second complex number, which is 5i. 2 times 5i gives us positive 10i. Now we're going to take our 3i and multiply it times 4 and 5i. So I in FOIL stands for inside, multiplying the inside terms. 3i times 4 gives us 12i. And then the L in FOIL stands for last, meaning we're multiplying the last term in each complex number. 3i times 5i gives us 15i squared. So after we use the FOIL method, we are left with 8 plus 10i plus 12i plus 15i squared. So before we can simplify this to a complex number, we first want to replace this I squared with its equivalent, -1. When we do so, 15 times -1 gives us -15. And now we have 2 real numbers and 2 imaginary numbers. So the third step, we combine the like terms. 8 minus 15, our real number, plus 10i plus 12i, our imaginary number, giving us a final answer of 8 minus 15, which is -7, plus 10i plus 12i, which is 22i. So that is how you go about multiplying complex numbers. Let's have you try a few practice questions. Question number 1. Find the product of 6 times -3 plus 7i. Question number 2. Find the product of -4i times 5 minus 8i. Question number 3. Find the product of 8 minus 2i times -3 plus 4i. In question number 4, find the product of -9 plus 3i times 2 minus 6i. Pause the video, answer these questions, and then press play when you're ready to begin. Question number 1. We're asked to find the product of 6 times negative 3 plus 7i. So step 1, distribute the 6 to each term in this complex number. 6 times negative 3 gives us negative 18. 6 times positive 7i is positive 42i. So the answer to question number 1 is negative 18 plus 42i. Question number 2, we're asked to find the product of negative 4i times 5 minus 8i. Step 1, distribute the negative 4i to each term. Negative 4i times 5 is negative 20i. Negative 4i times negative 8i is positive 32i squared. And now we want to replace I squared with negative 1, giving us 32 times negative 1, which is negative 32. So negative 4i times 5 minus 8i is equal to negative 32 minus 20i. Question number 3. You were asked to find the product of 8 minus 2i times negative 3 plus 4i. So since we're multiplying two binomials, we'll need to use the FOIL method to expand the expression. 8 times negative 3 is equal to negative 24. 8 times positive 4i is positive 32i. Negative 2i times negative 3 is equal to positive 6i. And negative 2i times positive 4i is equal to negative 8i squared. So now we'll want to replace I squared with negative 1, giving us negative 8 times negative 1, which is equal to positive 8. So we have two real numbers, negative 24 and positive 8. So we'll be combining those. And we add that to our imaginary numbers, 32i and 6i. So the final answer is negative 24 plus 8, which is equal to negative 16, plus 32i plus 6i, which is 38i. So we get negative 16 plus 38i. In question number 4, we were asked to find the product of negative 9 plus 3i times 2 minus 6i. So the first step, we'll use the FOIL method to expand the expression. So negative 9 times 2 gives us negative 18. Negative 9 times negative 6i gives us positive 54i. Positive 3i times 2 gives us positive 6i. And positive 3i times negative 6i gives us negative 18i squared. So now we'll want to replace I squared with its equivalent, negative 1, giving us negative 18 times negative 1, which is positive 18. Step 3, combine the like terms. Negative 18 plus 18 will wind up canceling each other out since they equal 0. And we combine 54i and 6i. 54i plus 6i is equal to 60i. So the final answer, negative 9 plus 3i times 2 minus 6i is equal to 60i. So that is how you go about multiplying complex numbers. Let's now discuss how to divide by a complex number. And to do so, we must first discuss the concept of a conjugate. The conjugate of a complex number is a result of changing the sign of the imaginary number from negative to positive or positive to negative. So let's say we have our complex number, a plus bi. We have our real number and our imaginary number. The conjugate of a plus bi is a result of switching the imaginary number sign from a plus to a minus. So the real number is left alone, but the sign of the imaginary number changes. This is also true if the real number is negative. The conjugate of a complex number with a negative real number, you keep that same negative real number and you switch the sign of the imaginary number. So let's say we had 2 plus 4i. The conjugate, you want to switch the plus to a minus, giving you 2 minus 4i. If you have negative 2 plus 4i, the negative 2 remains the same, but positive 4i becomes negative 4i. Now, why is this important? Multiplying complex numbers that are conjugates will result in the removal of the imaginary number. So when we divide by a complex number, if we multiply the denominator by its conjugate, we'll be able to switch it from a complex number in the denominator to a real number. So if we had a plus bi times a minus bi, you would get a times a, which is a squared. A times negative bi would be negative abi. Bi times a would give you plus abi. And bi times negative bi would give you negative b squared I squared. The negative abi and the positive abi cancel each other out, leaving you with just a squared minus b squared I squared. I squared is equal to negative 1. So negative b squared times negative 1 gives you positive b squared. So when you multiply a complex number times its conjugate, you are able to remove the imaginary number. And if a squared is a real number and b squared is a real number, such as two integers, we'll be able to combine them to simplify the expression. So for example, 3 plus 2i times 3 minus 2i will be equal to 3 squared plus 2 squared. So by multiplying this times its conjugate, we'll get 9 plus 4, which gives us 13. And thus, we'll be able to simplify our denominators from a complex number to an integer value. For division, instead of dividing the way we do traditionally, what we are going to do is multiply the numerator and the denominator by the conjugate of the denominator. Why do we do this? A couple of things. Any number divided by itself is equal to 1. So by multiplying this fraction times 1, we are not changing the value of the fraction by adding or subtracting numbers, for example. We are simply changing the way that we represent this value. So for example, if we had 10 divided by 2, that would be equal to 5. 10 divided by 2 and 5 are just different ways of representing each other. So by multiplying the numerator and the denominator by the same number, which in essence is multiplying it times 1, the result that we have is a number that will have a simpler denominator, which will then be able to simplify into a single complex number. So you have a complex number divided by a complex number, and the result will be a complex number. Well, let me now walk you through the steps of dividing 7i by 2 plus 4i to get to 14i over 20 plus 28 over 20. So let's say you're asked to find the quotient of 7i divided by 2 plus 4i. Step 1, multiply the numerator, 7i, by the conjugate of the denominator, 2 plus 4i. The conjugate is the result of changing this plus to minus. So for step 1, 7i times 2 gives you 14i. Then you have 7i times negative 4i, which gives you negative 28i squared. And now we multiply the denominator by the conjugate. So that's 2 times 2, which equals 4. 2 times negative 4i gives us negative 8i. 4i times 2 gives us 8i, which negates the negative 8i. And 4i times negative 4i is negative 16i squared. So the next step, we want to replace each I squared with negative 1, giving us negative 28 times negative 1, which is positive 28, and negative 16 times negative 1, which is positive 16. And we can add 4 to 16 to give us 20. So after we multiply 7i divided by 2 plus 4i times 2 minus 4i over 2 minus 4i, we wind up with 14i plus 28 over 20. So we divided a complex number by a complex number. And once we break this fraction up into two separate fractions, we wind up with a complex number. 28 over 20 is our real number, plus 14i over 20 is our imaginary number. So complex divided by complex gave us a single complex number. And now we can simplify the fraction even further, this fraction here. So 28 over 20, we can divide the numerator by 4 and the denominator by 4, and that would give us 7 over 5, plus 14 can be divided by 2 and 20 can be divided by 2. So this would be 7i over 10. So the quotient of 7i divided by 2 plus 4i is equal to 7 over 5 plus 7i over 10. So that is how you go about dividing by a complex number. Let's now have you try a few practice questions. Question number 1. Find the quotient of 2 divided by 3 minus 5i. Question number 2. Find the quotient of 4 plus 3i divided by 6 minus 2i. And question number 3. Find the quotient of 7 minus 13i divided by negative 2 plus 8i. Pause video, answer these questions, and then press play when you are ready to begin. Question number 1. We're asked to find the quotient of 2 divided by 3 minus 5i. Step 1, multiply the numerator 2 by the conjugate of the denominator. Since the denominator is 3 minus 5i, the conjugate is the result of switching this minus to plus. So the first step, multiply the numerator by the conjugate of the denominator, 3 plus 5i, would give us 2 times 3, which is equal to 6, and 2 times positive 5i, which is equal to positive 10i. And now the second step, multiply the denominator by the conjugate of the denominator. So 3 times 3 is equal to 9. 3 times positive 5i is equal to positive 15i. Negative 5i times 3 is equal to negative 15i. This negates the positive 15i, so those are removed. And negative 5i times positive 5i is equal to negative 25i squared. So after the second step, you will want to replace this I squared with negative 1, giving you negative 25 times negative 1, which is positive 25. 9 plus 25 is 34. So we can simplify this fraction, 6 plus 10i over 34, by first breaking it up. And then we can simplify it further by dividing this numerator by 2 and this denominator by 2. So this becomes 3 over 17 plus 10 can be divided by 2, and 34 can be divided by 2 as well, giving us 5i over 17. So the final answer for 2 divided by 3 minus 5i is 3/17 plus 5i/17. Question number 2. You were asked to find the quotient of 4 plus 3i divided by 6 minus 2i. Step 1, multiply the numerator by the conjugate of the denominator. Since the denominator is 6 minus 2i, the conjugate is 6 plus 2i. So 4 times 6 is equal to 24. 4 times positive 2i is positive 8i. Positive 3i times 6 is positive 18i. 18i plus 8i gives you 26i. And 3i times 2i gives you 6i squared. The second step, multiply the denominator, 6 minus 2i, by the conjugate of the denominator, 6 plus 2i. 6 times 6 is equal to 36. 6 times positive 2i is positive 12i. Negative 2i times 6 is equal to negative 12i, which cancels out the positive 12i. And negative 2i times positive 2i is negative 4i squared. So you'll now want to replace each I squared with negative 1. So here we get 6 times negative 1, which will be equal to negative 6. And negative 4 times negative 1 will be equal to positive 4. 24 minus 6 gives you 18 in the numerator. And 36 plus 4 gives you 40 in the denominator. So we have 18 plus 26i divided by 40. So we can simplify the fraction. First by splitting it up into two separate fractions. 18 divided by 40 plus 26i divided by 40. And you can simplify this further by removing 2 from the numerator and denominator of each of these terms, leaving you with 9 over 20 plus 13i over 20. Let's take a look at question number 3. We were asked to find the quotient of 7 minus 13i divided by negative 2 plus 8i. We first want to multiply the numerator by the conjugate of the denominator. The conjugate is the result of switching this plus to minus. So we're going to multiply the numerator and denominator by negative 2 minus 8i. When we do so, we multiply 7 times negative 2, and that gives us negative 14. 7 times negative 8i gives us negative 56i. Negative 13i times negative 2 gives us positive 26i. Negative 56i plus 26i gives us negative 30i. Negative 13i times negative 8i gives us positive 104i squared. So we have our numerator after step 1. Then we multiply the denominator by the conjugate, negative 2 minus 8i as well, giving us negative 2 times negative 2, which is positive 4. Negative 2 times negative 8i gives us positive 16i. Positive 8i times negative 2 gives us negative 16i, which cancels out the positive 16i. We multiply 8i times negative 8i, giving us negative 64i squared. So now that we've multiplied the numerator and the denominator by the conjugate of the denominator, we have two different I squared terms in our expression that we want to replace with negative 1. Positive 104 times negative 1 gives you negative 104. And negative 64 times negative 1 will give you positive 64 here. Negative 14 minus 104 will give you negative 118 in the numerator. and 4 plus 64 will give you 68 in the denominator. So we wind up with negative 118 minus 30i divided by 68. And the fourth step, you want to simplify this fraction. So you first break it up into two fractions. Negative 118 divided by 68 minus 30i divided by 68. And these can be simplified further by removing 2 from each term. We have all even numbers. Negative 118 divided by 68 becomes negative 59 over 34 minus 15i over 34. So that is how you go about dividing by a complex number. Let's now move on to the third section of the chapter. We'll now be discussing two different situations in which you'll be factoring polynomials and you'll wind up with complex numbers as roots. The first situation I wanted to discuss is when you have two squares, such as a squared and b squared. Now, the difference of two squares can be factored into a product of two real numbers. So a squared minus b squared is equal to a plus b, one factor, times a minus b, the second factor. But the sum of two squares can be factored into a product of two complex numbers, a plus bi times a minus bi. So let's say you had the difference between two squares, x squared and 3 squared, 9. This would be equal to the square root of the first term, which would be x. So you'll have an x in each of your factors. You're going to set up two sets of parentheses. The first term will be x. The second term will be the square root of 9, so that'll be 3. And the two factors should have two different signs between the x and the 3. So the factors of x squared minus 9 are x minus 3 and x plus 3. To confirm that this is true, we can FOIL out this expression. X times x gives us x squared. X times 3 gives us 3x. Negative 3 times x gives us negative 3x. And negative 3 times positive 3 gives us negative 9. Negative 3x and positive 3x cancel each other out, leaving us with x squared minus 9. Some other similar examples. X squared minus 25. How would you factor this polynomial? What is the square root of the first term? The square root of x squared is x, so that goes into each of the two factors. The square root of the second term, 25, is 5, so that goes into each of the two factors, and they are separated by the two different signs. Another example, x squared minus 36. What is the square root of the first term? X squared. That would be x. That goes into each factor. What is the square root of the second term? That would be 6. That goes into each factor. And they are separated by different signs. So again, the difference of two squares gives us factors that are real numbers. But if we had the sum of two squares, it's the same exact process, except our integers are imaginary numbers. So we attach an I to our integers. So for example, x squared plus 9. What is the square root of the first term? X squared. That would be x, so that goes into each factor. What is the square root of the second term? 9. That would be 3, so that goes into each factor. We multiply our integer by I in each factor, so we wind up with 3i. And just as we did with the difference in the sum of two squares, our factors should each have two different signs. I want them to be conjugates. To confirm this, we can FOIL this out. X times x gives you x squared. X times 3i gives you positive 3xi. Negative 3i times x gives you negative 3xi. And negative 3i times positive 3i gives you negative 9i squared. Negative 3xi and positive 3xi cancel each other out, leaving you with x squared minus 9i squared. And now we can replace I squared with negative 1. Negative 9 times negative 1 is positive 9. So we wind up with x squared plus 9, what we started with, thus confirming that these two are the factors of x squared plus 9. So the only difference between the sum of two squares and the difference of two squares, the sum of two squares have factors that are complex numbers, and you multiply your integer in each factor by I. So for example, x squared plus 25 would be equal to the square root of x squared, which is x in each factor. The square root of 25 is 5. That goes into each factor. Multiply each of those 5s by I. And then you separate the real numbers from the imaginary numbers with two different signs. Same with x squared plus 36. What is the square root of the first term? That would be x. What is the square root of the second term? That would be 6. Multiply the 6's by I. And then separate the x's and 6i's by two different signs. Now in some cases, the coefficient of our quadratic term will not be 1. In this case, the coefficient of the quadratic term must be a perfect square, and the square root will be the coefficient of the x in each factor. So for example, if you had 4x squared plus a squared, when you factor this expression, you'll take the square root of the first term. The square root of 4 is equal to 2. The square root of x squared is equal to x. So the first term in both factors is 2x. If the expression were 9x squared plus a squared, the square root of 9 would be 3, and the square root of x squared would be x. So 3x is the first term in each factor. In other cases, you'll have to remove a factor in order to create the sum of two perfect squares. So a common factor can be removed from each term to convert the polynomial into two perfect squares. Let's say you were given 18x squared plus 8. 18 is not a perfect square, and neither is 8. But if we remove 2 from each of these numbers, we'll get 18 divided by 2, which is 9, and 8 divided by 2, which is 4, which will give us 9x squared, which is a perfect square, plus 4, which is also a perfect square. And now we can factor the sum of the two squares the way we normally would, with the factor 2 on the outside. So let's walk through an example. Let's say you're asked to factor 4x squared plus 16 and check the answer. Step 1, create two sets of parentheses. These are where we'll put our factors. Step 2, place a positive sign in one factor and a negative sign in the other factor. And now we can continue to step 3, which is to add the square root of the first term to the left side in each factor. The square root of 4 is equal to 2. And the square root of x squared is equal to x. So 2x is the first term in each factor. And now step 4, add the square root of the second term, 16, to the right side in each factor. And the square root of 16 is 4. The next step, step 5, we want to multiply 4 in each factor by the imaginary unit I, showing us the factors of 4x squared plus 16 are equal to 2x plus 4i and 2x minus 4i. Now the last step, we can check the answer by multiplying the factors. The final polynomial must match the original polynomial, and we get 2x times 2x, which is 4x squared. 2x times negative 4i is negative 8xi. 4i times 2x is equal to positive 8xi, which negates negative 8xi. 4i times negative 4i is negative 16i squared. I squared is equal to negative 1. And negative 16 times negative 1 is positive 16. So since the final polynomial matches the original polynomial, this confirms that 4x squared plus 16 can be factored into 2x plus 4i times 2x minus 4i. Now that is how you go about factoring the sum of two squares. Let's now have you try a few practice questions. Question number 1, factor x squared plus 49 and check the answer. Question number 2, factor 9x squared plus 36 and check the answer. In question number 3, factor 32x squared plus 50 and check the answer. Pause the video, answer these questions, and then press play when you are ready to begin. Question number 1, we had x squared plus 49. Step 1, we want to create two sets of parentheses for our factors. In step 2, place a positive sign in one factor and a negative sign in the other factor. In step 3, we want to add the square root of the first term, x squared, to the left side in each factor. The square root of x squared will be x, so that's the first term in each factor. Step 4, add the square root of the second term to the right side in each factor. The square root of 49 is equal to 7. And now step 5, we want to multiply 7 by I. So we get x squared plus 49 can be factored into x plus 7i times x minus 7i. In step 6, we can check the answer by multiplying the factors. The polynomial that we get must be equal to the original polynomial, x squared plus 49, giving us x times x, which is x squared. X times negative 7i is negative 7xi. 7i times x is positive 7xi, which negates negative 7xi. 7i times negative 7i would give us negative 49i squared, and I squared is equivalent to negative 1. Negative 49 times negative 1 is equal to positive 49. So since our final polynomial matches the original polynomial, that confirms that x squared plus 49 can be factored into x plus 7i times x minus 7i. So that is the answer to question number 1. Let's now have a look at question number 2. We were given 9x squared plus 36. Step 1, we want to create two sets of parentheses for our factors. In step 2, we want to place a positive sign in one factor and a negative sign in the other factor. And now step 3, we want to add the square root of the first term, 9x squared, to the left side in each factor. And that would give us the square root of 9, which is 3, and the square root of x squared, which is x. So 3x is the first term in each factor. Now step 4, we go to the second term, 36, and we add the square root of 36 to the right side in each factor. And the square root of 36 is equal to 6. And now step 5, we multiply the number from step 4, which was 6, by the imaginary unit I. So we see 9x squared plus 36 can be factored into 3x plus 6i times 3x minus 6i. In step 6, we can check the answer by multiplying the factors. The final polynomial must match the original polynomial, giving us 3x times 3x, which is 9x squared. 3x times negative 6i is negative 18xi. 6i times 3x is positive 18xi, which negates negative 18xi. 6i times negative 6i is negative 36i squared. I squared is equivalent to negative 1. And negative 36 times negative 1 is equal to positive 36. So since the final polynomial matches the original polynomial, that confirms that 9x squared plus 36 can be factored into 3x plus 6i times 3x minus 6i. In question number 3, we were given 32x squared plus 50. Neither 32 nor 50 are perfect squares, so that's the hint that we'll need to remove a factor from both terms, and that factor would be 2. When we remove a common factor 2 from each term, we get 32 divided by 2, which is 16, as our new coefficient for the quadratic term, and 16 is a perfect square, so that works. 50 divided by 2 is equal to 25, which is also a perfect square. So now we can factor 16x squared plus 25 the way we normally would. So step 2, we want to create 2 sets of parentheses for this part of the polynomial here. And now step 3, you will want to place a positive sign in one factor and a negative sign in the other factor. Step 4, we'll add the square root of the first term, 16x squared, to the left side in each factor, giving us the square root of 16, which is 4, and the square root of x squared, which is x. So we get 4x as the first term in each factor. And now step 5, we'll add the square root of the second term, 25, to the right side in each factor. The square root of 25 is equal to 5. So we add 5 to both parentheses on the right side. And now step 6, we want to multiply the number from step 5, which was 5, by the imaginary unit I. And that will give us 32x squared plus 50 can be factored into 2 times 4x plus 5i times 4x minus 5i. And now, step 7, we can check the answer by multiplying the factors to confirm that the final polynomial that we get matches the original polynomial, 32x squared plus 50. We'll start by multiplying the factors in the parentheses, giving us 4x times 4x, which is 16x squared. 4x times negative 5i would give you negative 20xi. 5i times 4x would give you positive 20xi, which would cancel out negative 20xi. And 5i times negative 5i would give you negative 25i squared. I squared is equivalent to negative 1. And negative 25 times negative 1 is equal to positive 25. And now we multiply the 2 times this expression, giving us 2 times 16, which is 32x squared. And 2 times 25 would be 50. So since the final polynomial matches the original polynomial, that confirms that 32x squared plus 50 can be factored into 2 times 4x plus 5i times 4x minus 5i. And that is how you would go about factoring the sum of two squares. Let's now discuss how you would use the quadratic formula to find the roots in which a negative radicand is included. So the radicand is the number underneath our radical sign, and the imaginary unit I can be removed from a radical term with negative radicand because we can break it up into the product of two of its factors. So negative 1 times 9 equals negative 9. How does this help? Because now we can take the square root of 9, which is 3, and we can simplify. The square root of negative 1 is equal to I, giving us 3i. Whereas we wouldn't be able to proceed from here since we have a negative radicand. Same thing for negative 16. Negative 16 is the product of 16 times negative 1. So the square root of negative 16 can be broken up into the square root of 16, which is 4, and the square root of negative 1, which is our I. But we can also remove the negative even if the second factor is not a perfect square, such as 10. The square root of negative 10 is equal to the square root of 10 times the square root of negative 1. The square root of negative 1 is I, as we know. And the square root of 10 is already simplified. So you can get the square root of 10i. You can just remove the negative and turn it into an I outside of the radical. So do not feel like you can only remove it if the second factor is a perfect square. That is not the case. The quadratic formula, you may want to commit it to memory. If a quadratic expression cannot be factored, then the quadratic formula is used to find the values of the roots, our x's. So the quadratic formula tells us that x is equal to negative b plus or minus the square root of b squared minus 4ac divided by 2a. How does this help us? Well, let's walk through an example together. Let's say you were asked to solve for x and check the answers. For x squared minus 6x plus 25 is equal to 0. A couple of things. When you are using the quadratic formula, on the right side, make sure you have 0. If there is a constant here, move it to the left side and combine it with the constant on this side. Secondly, if you have an expression that cannot be factored the way we would do it normally, such as considering the factors of our constant and finding a pair that have a sum equal to the coefficient of our x. So the factors of 25 would be 5 and 5, and we can't combine those to get negative 6. We also can't combine 1 and 25 to get negative 6 either. So we cannot factor this the way we normally would. So we use the quadratic formula to find the value of x. Now in the quadratic formula, we have three variables, a, b, and c. A is equal to the coefficient of the x squared term. So when it is not shown, it is equal to 1. 1 times x squared is x squared. B is equal to the coefficient of the x term. So in this expression, it would be negative 6, sign included. And C is equal to the constant, which in this case is 25. So when we plug A, B, and C into the quadratic formula here, we get x is equal to negative 1 times negative 6 plus or minus the square root of negative 6 squared minus 4 times 1 times 25 divided by 2 times 1. And now we can simplify this to solve for x. Negative 1 times negative 6 is equal to positive 6 divided by 2 times 1, which is 2, plus or minus the square root of negative 6 squared, which is 36, minus 4 times 1 times 25, which is 100, divided by 2 times 1, which is 2. Remember, when you split up the fraction, the denominator stays with both. And now we can simplify this further. 6 divided by 2 is equal to 3, plus or minus the square root of 36 minus 100, which would be negative 64 over 2. The square root of negative 64 is equal to the square root of 64 times the square root of negative 1. So now we can simplify this to 8i. 8 divided by 2 is equal to 4. So we get x is equal to 3 plus or minus 4i. So we have two possible values that may work. So now what we want to do is check the answers by plugging each number into the original equation. So I'll plug in the smaller number 3 minus 4i first, and then we'll test 3 plus 4i. In the original equation, x squared minus 6x plus 25 is equal to 0. So we'll plug in 3 minus 4i here and here. And that gives us 3 minus 4i times 3 minus 4i minus 6 times 3 minus 4i plus 25 is equal to 0. We'll use the FOIL method to expand our x squared. 3 times 3 is equal to 9. 3 times negative 4i is negative 12i. Negative 4i times 3 is negative 12i. And negative 4i times negative 4i is 16i squared. Negative 6 times 3 is negative 18. Negative 6 times negative 4i is positive 24i. Plus 25 is equal to 0. Negative 12i minus 12i gives you negative 24i. 16 times I squared is 16 times negative 1. 24i. And we have 9 minus 18, which is negative 9. Plus 25 gives us positive 16 here. Negative 24i and positive 24i cancel each other out, leaving you with 16 times negative 1, which is negative 16, plus 16. Combine those and we get 0. So when we plug in 3 minus 4i for x, we get 0 is equal to 0. And since the left side equals the right side, this confirms that 3 minus 4i is a value of x. And now let's test the second possible value, 3 plus 4i. 3 times 3 gives us 9. 3 times 4i gives us 12i. 4i times 3 gives us 12i. 4i times 4i is 16i squared. Negative 6 times 4i is negative 24i. Plus 25 is equal to 0. 12i plus 12i is 24i. 16 times I squared is 16 times negative 1 minus 24i. And we have 9 minus 18, which is negative 9. Plus 25 is positive 16. 24i minus 24i cancel each other out, leaving us with 16 times negative 1, which is negative 16, plus 16, which is equal to 0. So this confirms that x also equals 3 plus 4i. So that is how you can use the quadratic formula to solve quadratic expressions that cannot be factored traditionally. Let's have you try a few practice questions. Solve for x and check the answers. Question number 1. X squared plus 4x plus 5 is equal to 0. Question number 2. X squared minus 2x plus 5 is equal to 0. And question number 3. X squared plus 6x plus 13 is equal to 0. Pause the video, answer these questions, and then press play when you are ready to begin. Question number 1. We're solving x squared plus 4x plus 5 is equal to 0. Always make sure that the right side is equal to 0. So that's taken care of. So we move on to A, the coefficient of x squared, so that's 1. B is the coefficient of x, which is positive 4. And C is our constant, positive 5. We plug A, B, and C into the quadratic formula, and we get x is equal to negative 1 times 4, plus or minus the square root of 4 squared, minus 4 times 1 times 5, divided by 2 times 1. And now we can simplify this expression to solve for x. Negative 1 times 4 is negative 4, divided by 2 times 1, which is 2, plus or minus the square root of 4 squared, which is 16, minus 4 times 1 times 5, which is 20. Negative 4 divided by 2 is negative 2, plus or minus the square root of 16 minus 20, which is negative 4, over 2. The square root of negative 4 is equal to the square root of 4 times the square root of negative 1. The square root of negative 1 is I, and the square root of 4 is 2. 2 divided by 2 is equal to 1. So we wind up with x is equal to negative 2 plus or minus I. And now we can check the answers by plugging each number into the original equation. So I'll plug in the smaller number, negative 2 minus I first, and then we'll check the larger number, negative 2 plus I second. So we plug negative 2 minus I in for x here and here, giving us negative 2 minus I times negative 2 minus I plus 4 times negative 2 minus I plus 5 is equal to 0. We use the FOIL method to expand our x squared. Negative 2 times negative 2 is positive 4. Negative 2 times negative I is positive 2I. Negative I times negative 2 is positive 2I. Negative I times negative I is positive I squared. 4 times negative 2 is negative 8. 4 times negative I is negative 4I. Plus 5 is equal to 0. 2I plus 2I is 4I. Minus 4I is equal to 0. Leaving us with 4. I squared is negative 1. Minus 8 plus 5. 4 minus 1 is equal to 3. 3 minus 8 is negative 5. And negative 5 plus 5 is equal to 0. 0 equals 0 proves that x does equal negative 2 minus I. And now we test our second potential value, negative 2 plus I. And we plug that in for x here and here, giving us negative 2 times negative 2, which is positive 4. Negative 2 times positive I is negative 2I. I times negative 2 is negative 2I. I times I is I squared. 4 times negative 2 is negative 8. 4 times I is 4I. Plus 5 is equal to 0. Negative 2I minus 2I is negative 4I. Plus 4I is equal to 0. Those cancel each other out, leaving you with 4. I squared is negative 1 minus 8 plus 5. 4 minus 1 is 3. 3 minus 8 is negative 5. Negative 5 plus 5 is equal to 0, proving that x does also equal negative 2 plus I. So the answer to question number 1 is negative 2 plus or minus I. Let's take a look at question number 2. We were given x squared minus 2x plus 5 is equal to 0. We have 0 on the right side, so we're ready to go. So we start with the coefficient of x squared, which is 1. The coefficient of x is negative 2, so that's b. And our constant is positive 5, so that's c. We plug a, b, and c into the quadratic formula and solve for x. So we get x is equal to negative 1 times negative 2 plus or minus the square root of negative 2 squared minus 4 times 1 times 5 divided by 2 times 1. And now we simplify this fraction to solve for x, giving us negative 1 times negative 2, which is 2, divided by 2 times 1, which is 2, plus or minus the square root of negative 2 squared, which is 4, minus 4 times 1 times 5, which is 20, 2 divided by 2 is equal to 1, plus or minus the square root of 4 minus 20, which is negative 16 over 2. The square root of negative 16 is equal to the square root of 16 times the square root of negative 1. The square root of 16 is 4, and the square root of negative 1 is I. 4 divided by 2 is equal to 2, giving us x is equal to 1 plus or minus 2i. In step 3, check the answers by plugging each number into the original equation. So we'll plug in 1 minus 2i first, in for x here and here, giving us 1 minus 2i times 1 minus 2i minus 2 times 1 minus 2i plus 5 is equal to 0. We'll use the FOIL method to expand our x squared. 1 times 1 is 1. 1 times negative 2i is negative 2i. Negative 2i times 1 is negative 2i. Negative 2i times negative 2i is positive 4i squared. Negative 2 times 1 is negative 2. Negative 2 times negative 2i is positive 4i. Plus 5 is equal to 0. Negative 2i minus 2i is negative 4i. And that cancels out positive 4i, leaving us with 1 plus 4 times negative 1 minus 2 plus 5. 4 times negative 1 is negative 4. 1 minus 4 is negative 3. Negative 3 minus 2 is negative 5. And negative 5 plus 5 is equal to 0. Left side equals right side proves that x does equal 1 minus 2i. And now we'll test our second potential value, 1 plus 2i. We'll plug it in for x here and here. We'll use the FOIL method to expand our x squared, giving us 1 times 1, which is 1. 1 times 2i is 2i. 2i times 1 is 2i. And 2i times 2i is 4i squared. Negative 2 times 1 is negative 2. Negative 2 times positive 2i is negative 4i. Plus 5 is equal to 0. 2i plus 2i is 4i. Minus 4i, so those cancel each other out, leaving you with 1 plus 4 times negative 1 minus 2 plus 5. 4 times negative 1 is negative 4, giving us 1 minus 4, which is negative 3. Negative 3 minus 2 is negative 5. And negative 5 plus 5 is equal to 0. 0 equals 0 proves that x also equals 1 plus 2i. So the answer to question number 2 is x is equal to 1 plus or minus 2i. And let's have a look at question number 3. X squared plus 6x plus 13 is equal to 0. A is equal to our coefficient of x squared, so A is equal to 1. B is equal to the coefficient of our x term, so it is positive 6. And C is equal to our constant, positive 13. We plug A, B, and C into the quadratic formula, and we get x is equal to negative 1 times 6 plus or minus the square root of 6 squared minus 4 times 1 times 13 divided by 2 times 1. And now we can simplify this fraction to solve for x. Negative 1 times 6 is equal to negative 6 divided by 2 times 1, which is 2, plus or minus the square root of 6 squared, which is 36, minus 4 times 1 times 13, which is 52, divided by 2 times 1, which is 2. Negative 6 divided by 2 is negative 3, plus or minus the square root of 36 minus 52, which is negative 16 over 2. The square root of negative 16 is equal to the square root of 16 times the square root of negative 1, which is equal to 4i. 4 divided by 2 is equal to 2. So we get x is equal to negative 3 plus or minus 2i. And now we will check the answers by plugging each number into the original equation. So I'll test the smaller number, negative 3 minus 2i first, and then I'll test negative 3 plus 2i second. We plug in negative 3 minus 2i for x here and here, giving us negative 3 minus 2i times negative 3 minus 2i plus 6 times negative 3 minus 2i plus 13 is equal to 0. Negative 3 times negative 3 is equal to 9. Negative 3 times negative 2i is equal to 6i. Negative 2i times negative 3 is 6i. And negative 2i times negative 2i is 4i squared. Plus 6 times negative 3, which is negative 18. 6 times negative 2i is negative 12i. Plus 13 is equal to 0. 6i plus 6i is 12i. Minus 12i is 0. So those negate each other, leaving you with 9 plus 4 times negative 1 minus 18 plus 13. 4 times negative 1 is negative 4. 9 minus 4 is 5. 5 minus 18 is negative 13. Negative 13 plus 13 is 0. So this shows that x does equal negative 3 minus 2i. And now we test our second potential value, negative 3 plus 2i, and we plug it in for x here and here. We'll use the FOIL method to expand our x squared. Negative 3 times negative 3 is 9. Negative 3 times positive 2i is negative 6i. 2i times negative 3 is negative 6i. And 2i times 2i is positive 4i squared. 6 times negative 3 is negative 18. 6 times 2i is 12i. Plus 13 is equal to 0. Negative 6i minus 6i is negative 12i. Plus 12i, so those cancel each other out, leaving us with 9 plus 4 times negative 1 minus 18 plus 13 is equal to 0. 4 times negative 1 is negative 4. 9 minus 4 is equal to 5. 5 minus 18 is equal to negative 13. And negative 13 plus 13 is equal to 0. So this shows that x also equals negative 3 plus 2i. So the answer to question number 3 is x is equal to negative 3 plus or minus 2i. And that is how we go about factoring using the quadratic formula. Let's now move on to graphing complex numbers. Since complex numbers are not on a number line, they cannot be plotted on a coordinate plane with x and y axes. So this is our normal coordinate plane. We have our x-axis. To the left of the y-axis, we have our negative real numbers. To the right, we have our positive real numbers. Above the x-axis, we have positive real numbers. And below the x-axis, we have negative real numbers along our y-axis. So on neither axis is there a place for our imaginary numbers, the square root of negative 1. So because of this, we'll need to use a complex plane instead. A complex plane has real numbers on the horizontal axis and imaginary numbers on the vertical axis. So now we can graph a complex number such as 2 plus 3i as a single point on a complex plane. You go along the real axis to positive 2, and then you go up along the imaginary axis to positive 3i. So this point here would represent the complex number 2 plus 3i. Another example, negative 4 minus 2i. The real number is negative 4. So you go to the real axis until you get to negative 4. And then the imaginary number is negative 2i. So you go down to negative 2i. So this point here represents the complex number, negative 4 minus 2i. And one more example, negative 7 plus 4i. You go to negative 7 along the real axis, and then you go up to positive 4 along the imaginary axis. And this point here would represent the complex number, negative 7 plus 4i. So now that you have an understanding of how to graph a complex number onto a complex plane, let's have you try a few practice questions. Question number 1, graph negative 4 plus 5i. Question number 2, graph negative 2 minus 2i. And question number 3, graph 3 plus 4i. Pause the video, answer these questions, and then press play when you are ready to begin. Question number 1, we wanted to graph negative 4 plus 5i. So step 1, go to negative 4 along the real axis. And then step 2, go up to 5 along the imaginary axis. The third step, plot the point. So this would represent negative 4 plus 5i. Question number 2, we were asked to plot negative 2 minus 2i. Step 1, go to negative 2 along the real axis. Step 2, go down to negative 2 along the imaginary axis, and then plot the point. So this point here would represent the complex number, negative 2 minus 2i. In question number 3, you were asked to plot the number 3 plus 4i. So step 1, go to 3 along the real axis. Step 2, go up to 4 along the imaginary axis, and then plot the point. So this point would represent 3 plus 4i. So that is how you go about graphing complex numbers onto a complex plane. Let's now discuss what a modulus is. The modulus, R, of a complex number is the distance from the origin to the complex number in the complex plane. So if we had a complex number, a plus bi, if you were to draw a line from that point to the origin, that would be the modulus. If you draw a dotted line from the complex number down to the real axis, you see that we wind up creating a right triangle. So along our real axis, we wind up going a distance of a from the origin to here, since that is our real number. And then the distance from the real axis up to the complex number is b, the value of the imaginary number. So we have a right triangle, and we know the values of two of the sides, a and b. So that will allow us to use trig to solve for our third side, r, or the modulus. But let's say we had the complex number 3 plus 4i. That means this distance along the bottom is 3, the real number, 3. And the distance of this leg is 4, the imaginary number 4. And then you use Pythagorean theorem to solve for r, which we'll get into in a second. But first, I just wanted to also note that the modulus r is also known as the absolute value of the complex number. In case the questions you are given are structured where they're asking you for the absolute value of the complex number, they are referring to the modulus. Throughout this chapter, though, I'll just be referring to it as the modulus, but I just wanted to make sure you were aware of this. So since a right triangle can be created in the complex plane, then the modulus can be calculated using the Pythagorean theorem. the Pythagorean theorem tells that for a right triangle, if we have sides A, B, and C, C being the hypotenuse, then A squared plus B squared would be equal to C squared. And if you're solving for C, the hypotenuse, you'd want to take the square root of both sides, giving you C is equal to the square root of A squared plus B squared. So for the modulus, R will be equal to the square root of A squared plus B squared, the real number and the imaginary number. So we are going to use this formula when solving for the modulus. R is equal to the square root of A squared plus B squared. So let's walk through an example. Let's say you were asked to find the modulus of the complex number 3 plus 4i. Step 1, square the real number, 3. So we'll plug in 3 for a here. So we get 3 squared. And the second step, square the imaginary number, which would be 4. You can leave the I out. And then you want to add the squares together. And then the fourth step, find the square root. So we wind up with R is equal to the square root of 3 squared plus 4 squared, which would be 9 plus 16. 9 plus 16 is equal to 25. And if R is equal to the square root of 25, then that means R is equal to 5. So that is how you would go about finding the modulus. Let's have you try a few practice questions. Question number 1. Find the modulus of -5 plus 2i. Question number 2. Find the modulus of 8 minus 6i. And question number 3. Find the modulus of 3 times -4 plus 6i minus 2i. Pause the video, answer these questions, and then press play when you are ready to begin. Question number 1. So to find the modulus, we'll use the formula R is equal to the square root of A squared plus B squared. So that helps us know that the first step is to square the real number, -5. Then the second step is to square the imaginary number 2. And then you add those squares together and then find the square root. So that lets us know R is equal to the square root of 25 plus 4. 4 plus 25 is equal to 29. So the answer to question number 1 is R is equal to the square root of 29. Question number 2, we wanted to find the modulus of 8 minus 6i. So step 1, square the real number 8. Step 2, square the imaginary number -6. Step 3, add the squares. In step 4, find the square root. So the modulus is equal to the square root of 64 plus 36. 64 plus 36 is equal to 100. And the square root of 100 is equal to 10. So the answer to question number 2 is R is equal to 10. Question number 3. We'll first have to expand and then simplify this expression to a complex number before we are able to plug the real number and the imaginary number into our formula. So the first step is to distribute the 3 to each term in this set of parentheses here. 3 times -4 is equal to -12. 3 times 6i is positive 18i. We then bring down the -2i. And 18i minus 2i gives us 16i. And now we can use -12 plus 16i to calculate the modulus. So step 3, square the real number, -12. Step 4, square the imaginary number 16. Step 5, you then add the squares and then find the square root. So the modulus is equal to the square root of negative 12 squared, which is 144, plus 16 squared, which is 256. 256 plus 144 is equal to 400. And the square root of 400 is equal to 20. So the modulus for negative 12 plus 16i is equal to 20. So that is how you go about calculating the modulus for a complex number. Let's now discuss what an argument is. The argument, theta, of a complex number is the angle made by the vector of the complex number and the positive real axis. So we have our positive real axis here. The argument, or the angle theta, is equal to the degrees from the positive real axis to our modulus, or the line that represents our modulus here. Now the argument is going to be the shortest angle that gets you from the positive real axis to the vector of the modulus. So in quadrants 1 and 2, you'll be moving counterclockwise. That'll be the shortest way to get to the vector. In quadrants 3 and 4, you'll be moving clockwise, since this will be the shortest angle to get to our vector. We'll discuss that more as we move along. Now, since we were dealing with right triangles, as we saw when we were looking at the modulus, the trigonometry function sine, cosine, and tangent can be used to find the argument theta. So quick review, remember SOHCAHTOA helps us understand the relationship between the angle we are looking at and the three sides of the triangle. So SO means the sine of theta is equal to the opposite side over the hypotenuse. So we have our angle theta, the side opposite over the hypotenuse of the triangle. Ka represents the cosine of the angle, which in this case is theta. So ka is cosine adjacent hypotenuse. So the cosine of theta is equal to the adjacent side divided by the hypotenuse. Adjacent by hypotenuse. And TOA lets us know the tangent of the angle is equal to the opposite side over the adjacent side. Opposite over adjacent. Now, if the complex number is known, then use the arctan or inverse tangent to find the value of theta. So, if we have some complex number, a plus bi, this side is going to have a length of a, equivalent to our real number along our real axis. B is the length of this second side here, or the opposite side of our theta. Since b is along the imaginary number, it's the same value as this imaginary number. So if we're looking to figure out, do we use sine, cosine, or tangent? Well, if we look at SOHCAHTOA in relation to our sides, a, b, and r, tangent of theta is the one that we can use just by having the complex number. Sine of theta is equal to b over r, opposite b over hypotenuse r. But if we know the complex number, we would then have to calculate the modulus to figure out theta here. So we want to skip that step, calculating the modulus. Cosine of theta is equal to the adjacent side over the hypotenuse, or modulus. Again, we don't want to have to calculate the modulus when finding the argument. So that is why we use tangent. Since tan of theta is equal to b over a, just by having the complex number, we'll then have a and b every time. Thus, we'll be able to use tan theta for b over a. So the inverse tangent of theta will then give us what the angle is. So the tangent of theta provides the ratio of b over a, but the inverse tangent provides the actual angle in degrees. Now the arctangent or the inverse tangent, provides the angle that has a tangent of b over a in the first quadrant. And I say the first quadrant because as we move to the other quadrants, these rules will slightly change. Okay, but in quadrant 1, the theta angle is shortest from the real axis to the vector of our modulus. So the arctan of b over a will always give us theta in degrees in quadrant 1. And remember, arctan is equivalent to the inverse tangent. This is what the button on your calculator probably looks like. So throughout this video, we'll be using inverse tangent as opposed to arctan, but just know they are equivalent. Now, degrees versus radian. We'll be providing each answer in both degrees and radian throughout the rest of this chapter. Quick review. 1 revolution or circle is equivalent to 360 degrees or 2 radians. So if you start here, the positive real axis, that's considered 0 degrees. You move through quadrant 1, which is a total of 90 degrees. You move through quadrant 2, which is another total of 90. So now we're at 180 degrees. You move through quadrant 3, which is another 90 degrees, getting us to 270 degrees. And you move through quadrant 4, the final 90 degrees, to give us 1 circle, or 360 degrees total. 2 radian means you start at 0. You go halfway around, so that's 1 radian. You go the remaining half around, so you get to 2 radian. So that means halfway between 0 and 1 radian, we have half a radian. And halfway between a radian and 2 radian, we have 1.5, or 3 pi over 2 here. 1 radian is equal to pi, which is equal to 180 degrees. And 2 radians is equal to 2 pi, which is equivalent to 360 degrees. And this information is helpful because if we want to convert an angle from degree to radian measure, then we multiply the angle by pi over 180 degrees. Why is that? We see pi, which is equivalent to 1 radian, is equal to 180 degrees. So if we multiply an angle by pi over 180 degrees, since pi is equivalent to 180 degrees, we are actually multiplying that angle by 1. Any number divided by itself is equal to 1. So we are not changing the actual value of the angle. We are changing how we represent that value. We're changing it from degrees to radian. So let's take a look at this. If you found an argument that was 80 degrees and you wanted to change it to radian form, 80 degrees times pi over 180 degrees is equal to 80 divided by 180, which is 0.44 radian. 120 degrees in radian form would be 120 degrees divided by 180 degrees, which would be 0.66 radian. And 220 degrees divided by 180 degrees would be 1.22 radian. So we'll use pi over 180 degrees to convert our arguments from degree measure to radian form so that you can answer the questions that your instructor asks you in either or both forms. Let's say you're asked to find the argument of 3 plus 4i. So this would be in quadrant 1. When you are calculating the argument, you should always sketch out the right triangle that you are working with so that you can confirm what quadrant you are working with, which will make it easier to avoid making any small mistakes when calculating theta. So we'll first start by finding the argument in quadrant 1 for 3 plus 4i. So step 1, go to 3 on the real axis. Step 2, draw a dotted line up to 4 on the imaginary axis. And then step 3, plot the point. So this point represents 3 plus 4i. And then from the point to the origin, you want to draw a line. By doing so, we've now created a right triangle in quadrant 1. That lets us know that this angle here, closest to the origin, is our theta, or the argument that we are looking for. The angle from the positive real to the vector of our modulus is equal to theta. So now that we have our right triangle, we know that the adjacent side to theta is 3, our real number, and the side opposite of theta is 4, the imaginary number. And with our right triangle, we can now use the inverse tangent of theta, which should be opposite over adjacent, or 4 over 3, to find out what theta is. So step 5, find the inverse tangent of 4 over 3 with a calculator in degrees mode. You plug that in, and you get theta is equal to 53 degrees. And if you want this answer in radian form, multiply the answer by pi over 180 degrees. 53 degrees divided by 180 degrees is equal to 0.29 radian. So the answer would be 53 degrees, or 0.29 radian. Let's have you complete a few practice questions. Question number 1. Find the argument of 2 plus 6i. Question number 2. Find the argument of 4 plus 5i. And question number 3. Find the argument of 3 plus 7i. Pause the video, answer these questions, and then press play when you are ready to begin. Question number 1, we're asked to find the argument of 2 plus 6i. Step 1, go to 2 on the real axis. Step 2, draw a dotted line up to 6 on the imaginary axis. And then step 3, plot the point. Step 4, draw a line from the point to the origin, creating our right triangle, letting us know that this angle closest to the origin is theta, our argument. So we create our right triangle that has an adjacent side equal to the real number, which is 2, and an opposite side equal to the imaginary number, which is 6. So now the 5th step, find the inverse tangent of the opposite over adjacent, which would be 6 over 2, with the calculator in degrees mode. So we get theta is equal to the inverse tangent of 6 over 2, which gives us theta is equal to 72 degrees. And to get this answer into radian form, we want to multiply it by pi over 180 degrees, giving us 72 degrees divided by 180 degrees, which is 0.4 radian. So the answer to question number 1 is 72 degrees and 0.4 radian. Question number 2, you're asked to find the argument of 4 plus 5i. Step 1, go to 4 on the real axis. Step 2, draw a dotted line up to 5 on the imaginary axis. Step 3, plot the point. Step 4, draw a line from the point to the origin, letting us know that this angle here is our theta, or our argument, which means our right triangle has a side adjacent to theta that is equivalent to 4, the real number, and a side opposite of theta, which is 5, the imaginary number. So that lets us know in order to find theta, you find the inverse tangent of opposite over adjacent, which is 5 over 4. And you do so with a calculator in degrees mode. So we plug in theta is equal to the inverse tangent of 5 over 4. And we get theta is equal to 51 degrees, which is located in quadrant 1. And to get this answer in radian form, multiply 51 degrees by pi over 180 degrees. 51 degrees divided by 180 degrees is equal to 0.29 radian. So the answer to question number 2 is 51 degrees or 0.29 radian. Question number 3, you were asked to find the argument of 3 plus 7i. Step 1, go to 3 on the real axis. Step 2, draw a dotted line up to 7 on the imaginary axis. And step 3, plot the point. Step 4, draw a line from the point to the origin, letting us know that this angle here is our argument, or theta. And since we now have our right triangle, we see that the side adjacent to theta is 3, and the side opposite of theta is 7. So finding the inverse tangent of 7 over 3 with the calculator in degrees mode will give us our argument, or theta. So the inverse tangent of 7 over 3 shows us that theta is equal to 67 degrees. And in radian form, you multiply 67 degrees by pi over 180 degrees. 67 degrees divided by 180 degrees is 0.37 radian. So the answer to question number 3 is 67 degrees or 0.37 radian. And that is how you find the argument of a complex number in quadrant 1. Let's now discuss how you find the argument of a complex number in quadrant 2. So remember, the argument theta is the smallest angle from the positive real axis to the vector of the modulus. So if this angle here is 25 degrees, if you were to go clockwise in the opposite direction, it would be 360, the total for one revolution, minus theta, the 25 degrees, which means this angle would be 335 degrees. So we know theta, or the argument, is always going to be counterclockwise, moving from the real axis in quadrant 1. Same thing in quadrant 2. The angle from the positive real axis to the vector of the modulus will always be shortest moving counterclockwise, because moving clockwise will always require going more than 180 degrees. Moving counterclockwise will always require going less than 180 degrees. So for example, if theta was 125 degrees this way, from here going clockwise, it would be 360, the total, minus 125, this angle, which means the remaining, this angle would be 235 degrees. So this angle is larger than this one, letting us know that theta here is our argument. Now, something interesting about quadrant 2, if the complex number is in the second quadrant, then subtract the alpha angle from 180 degrees to find the argument theta. So what does that mean? If we have a complex number that is in quadrant 2, so remember it's 1, 2, 3, 4. In quadrant 2, if we draw a dotted line from the complex number down to our real axis, our right triangle has an angle closest to the origin that is not our argument. Remember, the argument, or theta, is the angle from the positive real axis to the vector of our modulus. So we represent this angle for the right triangle as alpha. So in order to calculate our argument theta, it is the total 180 degrees here minus the alpha angle. So the remaining will be our argument. So 180 degrees minus the alpha angle is equal to theta. Calculating alpha, we'll still use the inverse tangent, or the opposite side over the adjacent side, to figure out what the alpha is, just like we did in quadrant 1 for theta. Except here we'll calculate alpha and then subtract it from 180 degrees. Now, one more thing to note. To find the inverse tangent of the alpha angle, use the absolute value of the opposite side divided by the adjacent side. In the second quadrant, the real number will be negative, but when you're using the inverse tangent, we're referring to the lengths of the side. So although in the complex number, the real number is negative, when we are calculating alpha, the adjacent side is going to remain positive, and the imaginary side will already be positive. All right, so ignore the negative for the real number when you're calculating the actual angle. Let's take a look at -4 plus 3i. So if you're asked to find the argument, step 1, go to -4 on the real axis, and step 2, draw a dotted line up to 3 on the imaginary axis, and then plot the point. Step 4, draw a line from the point to the origin. So we have our right triangle, and this angle here is our alpha angle, which means our right triangle has an adjacent side to the alpha angle that has a length of 4, the real number, and an opposite side equal to 3, the imaginary number. So now that we have this right triangle, we know that this angle here is our alpha, and the remaining angle along the real axis would then be our theta, or our argument. So we'll first need to calculate the alpha angle using the inverse tangent of the opposite side over the adjacent side, which would be 3/4. So we find the inverse tangent of 3/4 with a calculator in degrees mode, giving us that alpha is equal to the inverse tangent of 3/4, which shows us that alpha is equal to 37 degrees. When we subtract the alpha angle from 180 degrees, we get theta is equal to 143 degrees. If you wanted to get this answer into radian form, you multiply it by pi over 180 degrees. 143 degrees divided by 180 degrees gives you 0.79 radian. So the answer would be 143 degrees, or 0.79 radian. So that is how you go about finding the argument in the second quadrant. Let's have you complete a few practice questions. Question number 1. Find the argument of -5 plus 3i. Question number 2. Find the argument of -2 plus 4i. And question number 3. Find the argument of -6 plus 8i. Pause the video, answer these questions, and then press play when you are ready to begin. Question number 1, we're asked to find the argument of -5 plus 3i. So step 1, go to -5 on the real axis. Step 2, draw a dotted line up to 3 on the imaginary axis, and then plot the point. You then draw a line from the point to the origin, creating a right triangle, and the angle closest to the origin is our alpha angle. So the alpha angle has a side adjacent to it with a length of 5, the real number. And the alpha angle has a side opposite of it that is equal to 3, the imaginary number. And with this being our alpha angle, that lets us know from here to the positive real axis is our argument, or theta. So the fifth step, we'll find the inverse tangent of 3/5 to find our alpha. And then we'll subtract that from 180 degrees to find our theta. So the inverse tangent of alpha is 3/5. So the alpha angle is equal to 31 degrees. Subtract that from 180 degrees, and you get theta is equal to 149 degrees. To get this in radian form, multiply it by pi over 180 degrees. 149 degrees divided by 180 degrees is 0.83 radian. So the answer to question number 1 is 149 degrees, or 0.83 radian. Question number 2, we're asked to find the argument of -2 plus 4i. Step 1, go to -2 on the real axis. Step 2, draw a dotted line up to 4 on the imaginary axis. Step 3, plot the point. And then the fourth step, draw a line from the point to the origin, creating a right triangle. Our alpha angle is here, which means we have a right triangle with an adjacent side to the alpha angle that has a length of 2 and an opposite side equal to 4. So here is our alpha, which means our theta or argument is here. So we must first find the inverse tangent of the opposite side 4 over the adjacent side 2 with a calculator in degrees mode to find the alpha angle. So the alpha angle is equal to the inverse tangent of 4 over 2, which means the alpha angle is equal to 63 degrees. Subtracting that from 180 degrees gives us the argument is equal to 117 degrees. And in radian form, multiply 117 degrees by pi over 180 degrees. 117 degrees divided by 180 degrees is 0.65 radian. So the answer to question number 2 is 117 degrees, or 0.65 radian. Question number 3. You were asked to find the argument of -6 plus 8i. Step 1, go to -6 on the real axis. Step 2, draw a dotted line up to 8 on the imaginary axis. Step 3, plot the point. Step 4, draw a line from the point to the origin, letting us know that this angle closest to the origin is alpha. And our right triangle has an adjacent side equal to 6 and an opposite side equal to 8. So if this is our alpha angle, we'll calculate that using these sides. And then we'll subtract our alpha angle from 180 degrees to get the theta angle, our argument. So to find the inverse tangent of the opposite side over the adjacent, you do inverse tangent of 8 over 6. So the alpha angle is equal to 53 degrees. And now subtract that from 180 degrees. 180 degrees minus 53 degrees gives us a theta, or argument, of 127 degrees. And in radian form, multiply this by pi over 180 degrees. 127 degrees divided by 180 degrees is 0.71 radian. So question number 3, the argument is 127 degrees, or 0.71 radian. So that is how we go about finding the argument in the second quadrant. Let's now discuss how to find the argument in the third quadrant. Again, the argument, or theta, is the smallest angle from the positive real axis to the vector of the modulus. So previously we were moving counterclockwise to get to the vector of the modulus, but in this case it would always require us to go beyond 180 degrees, which means moving counterclockwise from the real axis is not the way we want to go when we are finding the argument in the third quadrant. Instead, we want to move clockwise to get to the vector of the modulus. That will now be our theta, or argument. When we do so, we'll wind up creating a right triangle by drawing a dotted line up to the real axis as we normally do. And that creates an angle closest to the origin. So we'll use our alpha angle again. So we'll calculate the alpha angle and subtract it from 180 degrees to find our argument, just as we did previously in quadrant 2. Except one difference is the argument will be negative since the smallest angle to the vector of the modulus is found by moving clockwise. Previously we were moving counterclockwise and all of our angles were positive. Since we're moving in the opposite direction now, which is clockwise, the angles will now be negative. So the range of values will be from 0 to positive 180 degrees, or from 0 to negative 180 degrees for all arguments. And again here, we will calculate negative theta by subtracting alpha from 180 degrees. So we'll do 180 minus alpha, but we'll still need to multiply the value that we get times negative 1 in order to get theta, because all of our angles now in quadrant 3 must be negative. So let's take a look at an example. If the alpha angle were 30 degrees, then the argument is going to wind up being negative 150 degrees. If the alpha angle comes out to be 20 degrees, then the argument, or theta, will wind up being negative 160 degrees. So the net total will be 180, but the theta angle, or the argument, must be negative. So let's say we were asked to find the argument of negative 4 minus 3i. We're going to draw our right triangle. So step 1, go to negative 4 on the real axis. Step 2, draw a dotted line down to negative 3 on the imaginary axis, and then plot the point. The fourth step, draw a line from the point to the origin. The angle closest to the origin is our alpha angle. So the side adjacent to the alpha angle has a length of 4, the real number. And the side opposite of alpha is 3, the net value of the imaginary number. And if this is our alpha, then from here to the positive real axis is our argument, or theta. So we'll first find the inverse tangent of the alpha angle. So you'll want to do the opposite side over the adjacent. So you find the inverse tangent of 3 over 4 with the calculator in degrees mode, and that lets you know that the alpha angle is equal to 37 degrees. Subtract that from 180 degrees, and 180 minus 37 degrees gives us 143 degrees. This is negative theta. We want to multiply negative theta by negative 1 because our argument is going to be negative in quadrant 3. When we multiply 143 degrees times negative 1, we get that theta, or the argument, is equal to negative 143 degrees. And in radian form, multiply it by pi over 180 degrees. So negative 143 degrees divided by 180 degrees gives you an argument equal to negative 0.79 radian. So that is how you go about finding the argument in quadrant 3. Let's now have you try a few practice questions. Question number 1, find the argument of negative 2 minus 5i. Question number 2, find the argument of negative 3 minus 10i. And question number 3, find the argument of negative 7 minus 2i. Pause the video, answer these questions, and then press play when you are ready to begin. Question number 1, we want to find the argument of negative 2 minus 5i. So step 1, go to negative 2 on the real axis. Step 2, draw a dotted line down to negative 5 on the imaginary axis. And step 3, plot the point. Step 4, draw a line from the point to the origin, creating our right triangle. And the alpha angle is closest to the origin here. So our right triangle has an alpha angle with an adjacent side equal to 2 and an opposite side equal to 5. And if this is our alpha, then this is our argument, or theta. So to find alpha, you'll want to find the inverse tangent of 5 over 2, opposite over adjacent. So that lets us know that the alpha angle is equal to the inverse tangent of 5 over 2, which is equal to 68 degrees. So when we subtract the alpha angle from 180 degrees, we get the negative theta angle is equal to 112 degrees. We then want to multiply negative theta by negative 1. So 112 degrees times negative 1 shows us that the argument, or theta, is equal to negative 112 degrees. And now if we want this in radian form, we'll multiply it by pi over 180 degrees. Negative 112 divided by 180 degrees will give you theta is equal to negative 0.62 radian. So the answer is negative 112 degrees, or negative 0.62 radian. Question number 2. You are asked to find the argument of negative 3 minus 10i. Step 1, go to negative 3 on the real axis. Step 2, draw a dotted line down to negative 10 on the imaginary axis, and then plot the point. The fourth step, you then draw a line from the point to the origin to create a right triangle. And now the angle closest to the origin is going to be our alpha angle. So our right triangle has an adjacent side to alpha that is equal to 3, and a side opposite of the alpha angle with a length of 10. And if this is our alpha angle, then from this vector to the positive real axis is our theta, or argument. So we'll use the inverse tangent of the opposite side over the adjacent side to find alpha, and then subtract that from 180 degrees. So the inverse tangent of 10 over 3 shows us that the alpha angle is equal to 73 degrees. Subtract that from 180 degrees, and we see that the negative theta is equal to 107 degrees. And if we multiply negative theta by negative 1, we get 107 degrees times negative 1, which means our theta, or argument, is equal to negative 107 degrees. And now we'll want to multiply the answer by pi over 180 degrees. 107 divided by 180 shows us that theta is equal to negative 0.59 radian. So the answer to question number 2 is negative 107 degrees, or negative 0.59 radian. In question number 3, we're asked to find the argument of negative 7 minus 2i. So step 1, go to negative 7 on the real axis. And step 2, draw a dotted line down to negative 2 on the imaginary axis, and then plot the point. Draw a line from the point to the origin, creating our right triangle in quadrant 3, and closest to the origin as our angle alpha, giving us a right triangle with an adjacent side to alpha with a length of 7, and a side opposite of alpha equivalent to 2. So now we have our alpha angle and our argument. So we'll use the inverse tangent of the opposite side 2 divided by the adjacent side 7 to find our alpha angle, and then we'll subtract that from 180 degrees to get our negative theta. So the inverse tangent of 2 over 7 shows that the alpha angle is equal to 16 degrees. Subtract the alpha angle from 180 degrees, and that shows us that negative theta is equal to 164 degrees. We then want to multiply negative theta by negative 1 to get theta. So theta is equal to 164 degrees times negative 1, which lets us know that theta, or the argument, is equal to negative 164 degrees. And if we would like this answer in radian form, we want to multiply it by pi over 180 degrees. Negative 164 divided by 180 degrees shows that theta, or the argument, is also equal to negative 0.91 radian. So the answer is negative 164 degrees, or negative 0.91 radian. So that is how you go about finding the argument in the third quadrant. Let's wrap up the chapter by discussing how we find the argument in the fourth quadrant. Now, as we've discussed, the argument, or the theta angle, is the smallest angle from the positive real axis to the vector of the modulus. And in the fourth quadrant, the argument is going to be negative since we are moving clockwise. When we moved counterclockwise in quadrants 1 and 2, the arguments were positive. So since we're moving in the opposite direction, the argument will be negative. So let's say we were asked to find the argument of 3 minus 4i. Step 1, we would go to 3 on the real axis. Step 2, we draw a dotted line down to negative 4 on the imaginary axis. And we plot the point here as a third step. And then draw a line from the point to the origin for step 4, creating our right triangle. Now, one thing to note, in the fourth quadrant, when we draw our right triangle, the angle closest to the origin in the triangle is the same angle that is the smallest angle from the positive real axis to the vector of the modulus. So in the fourth quadrant, this is theta, not alpha. In the third quadrant, when we drew our right triangle, the angle closest to the origin inside of that triangle was not our argument or theta, but in the fourth quadrant it is. So we will not need to calculate an alpha angle in the fourth quadrant. So we have our right triangle, and the side opposite is equal to 4, the length of the imaginary number. The side adjacent is 3, the real number. Now, one thing to keep in mind though is once we find the inverse tangent of this angle, that will give us a positive angle. We'll still need to multiply that angle by negative 1, since our argument in this quadrant will always be negative. So we'll find the inverse tangent of the opposite side over the adjacent, which is 4 over 3, giving us negative theta is equal to the inverse tangent of 4 over 3. When you plug that into your calculator, we get that negative theta is equal to 53 degrees. So to get theta, we want to multiply both sides by negative 1, giving us theta is equal to 53 degrees times negative 1, which means theta, or our argument, is equal to negative 53 degrees. And to get this answer into radian form, we want to multiply negative 53 degrees by pi over 180 degrees. When we do so, negative 53 degrees divided by 180 degrees gives us negative 0.29 radian. So the answer would be negative 53 degrees, or negative 0.29 radian. Let's have you try a few practice questions. Question number 1. Find the argument of 7 minus 7i. Question number 2. Find the argument of 5 minus 3i. Question number 3. Find the argument of 2 minus 9i. Pause the video, answer these questions, and then press play when you are ready to begin. Question number 1, we want to find the argument of 7 minus 7i. Step 1, go to 7 on the real axis. Step 2, draw a dotted line down to negative 7 on the imaginary axis. And the third step, plot the point. We then want to draw a line from the point to the origin so that we can create our right triangle in the quadrant. And this angle closest to the origin is our theta, or our argument that we're looking to calculate. With our right triangle, we see the side opposite is 7 and the side adjacent is 7. So we'll find the inverse tangent of 7 over 7 to get our negative theta. The inverse tangent of 7 over 7 is equal to 45 degrees. And since we know in quadrant 4, our theta must be negative, we'll multiply negative theta by negative 1 to get theta. So the argument is equal to 45 degrees times negative 1, which means the argument is equal to negative 45 degrees. And to get this answer in radian form, you'll want to multiply negative 45 degrees by pi over 180 degrees. Negative 45 degrees divided by 180 degrees shows us that the argument is equal to negative 0.25 radian. So the answer to question number 1 is negative 45 degrees and negative 0.25 radian. Question number 2, find the argument of 5 minus 3i. So step 1, go to 5 on the real axis. Step 2, draw a dotted line down to negative 3 on the imaginary axis. In step 3, plot the point. Step 4, draw a line from the point to the origin, creating a right triangle. The angle closest to the origin here, this is going to be our argument. And the side opposite of theta is 3. The side adjacent is 5. So when we find the inverse tangent of the opposite over adjacent, it's 3 over 5. Giving us negative theta is equal to the inverse tangent of 3 over 5. When you plug that in, you get negative theta is equal to 31 degrees. So to get theta, we want to multiply both sides by negative 1, giving us positive theta is equal to 31 degrees times negative 1, which shows us that the argument, or theta, is equal to negative 31 degrees. And to get this answer into radian form, you want to multiply negative 31 degrees by pi over 180 degrees. When we do so, negative 31 degrees divided by 180 degrees gives us negative 0.17 radian. So the answer to question number 2 would be negative 31 degrees and negative 0.17 radian. Question number 3. We're asked to find the argument of 2 minus 9i. Step 1, go to 2 on the real axis. Step 2, draw a dotted line down to negative 9 on the imaginary axis, and then plot the point. You then want to draw a line from the point to the origin, creating a right triangle. The angle closest to the origin here is going to be the argument we are looking for. And we see with our triangle, the side opposite of the angle is 9, the side adjacent is 2. So when we find the inverse tangent, it'll be 9 over 2. That gives us negative theta is equal to the inverse tangent of 9 over 2. And once you plug that into your calculator, you get negative theta is equal to 77 degrees. So to get theta, we want to multiply both sides by negative 1. Giving us theta is equal to 77 degrees times negative 1, which shows us that theta, or the argument, is equal to negative 77 degrees. And to convert this answer into radian form, you want to multiply negative 77 degrees by pi over 180 degrees. Negative 77 degrees divided by 180 degrees gives us theta is equal to negative 0.43 radian. So the answer to question number 3 is negative 77 degrees and negative 0.43 radian. And that wraps up this chapter on complex numbers. Should you have any follow-up questions, feel free to leave them in the comment section. Or you can contact a tutor in your neighborhood by visiting bookandtable.com or by downloading our app on the App Store. Peace.